Hello, everyone, and thank you for joining our presentation today on combiner boxes, carving out costs by maximizing both efficiency and safety. My name is Brian Bucci, and I'll be the moderator today. Please feel free to ask questions throughout the presentation. We ask that you suggest questions via the chat feature, which is located in the top toolbar of your screen. We'll be handling questions about halfway through the presentation and then again at the end. I also want to remind everyone that this webinar is being recorded and it will be housed on SunLink's website. I'd now like to introduce our speaker today, Mr. Daniel Sherwood. Daniel Sherwood is a professional electrical engineer with over a decade of experience in the solar industry. He's SunLink's Director of Electrical Products and Regulatory Compliance, and is also the chair on the UL 2703 Standard Technical Panel. Daniel designed his first solar combiner box for Powerlight in 2002, and many of the design elements that he pioneered are still in use today. Please welcome Daniel Sherwood.
Thanks, Brian. So I'm just going to go over the agenda quickly, what we're going to try and cover in the next 40 minutes or so, to try and leave some time at the end for questions. I'm going to cover a couple definitions just so we're on the same page. Then we're going to talk in general about how overcurrent protection devices work in current-limited circuits like in photovoltaic circuits. Then we're going to get right into combiner boxes, and we're going to talk about how to specify combiner box ratings, keeping the cost in mind. We're going to pause briefly for Q&A. I'll take just a couple questions there, and then we'll move on to combiner box safety, how to specify output lugs and terminals for combiner boxes. We'll talk then about how to design with the output circuit for combiner boxes, keeping costs in mind. Then I'll summarize everything we've learned and cover a couple quick things, and then we'll go right to Q&A at the end. So hopefully we'll have time to answer some questions. Definitions. Hopefully everyone is clear on this. This is from the National Electrical Code, but a source circuit is defined as the conductor that goes between a string of PV modules to a combiner box, often called a source circuit combiner box for that reason. And then the output circuit is defined as the conductor between the combiner box and typically an inverter or a recombiner, subcombiner box further down the line. So let's talk a little bit about how overcurrent protection devices work in current-limited circuits. So if we take this example, we have a string of PV modules in series, and we have a fuse, and we have a fault that happens between those modules and the fuse. The question I have for you is, will this fuse provide any protection in the circuit against this fault? And hopefully everyone can see the answer here is no, because the fuse comes after the fault, so it's not going to do anything for you. But let's look at the second scenario where we have a fault that comes after the fuse. So you have a string of modules, a fuse, and then a fault. Will that fuse provide any protection? And this is important because in a typical AC circuit, it would. If you have a fault after a fuse, the fuse will blow and clear that fault. But in a PV circuit, it will not. It actually does not provide any protection against that fault. And this is the reason why. Basically, PV modules, their operating current is very, very close to what their maximum potential current output is. They call that an inherently current-limited circuit. So if you look at a typical fuse rating for a string of solar modules, you'll take your short circuit current times 1.56, round up to the nearest fuse size, you end up with typically a 15-amp fuse in your combiner box. And the short circuit current that string can produce is only maybe 8.7 amps typically. So even if I have a fault here, it's not going to clear, it's not going to cause that fuse to blow. Hopefully everyone's on the same page here. Let's look at a second scenario. Here I have two strings and they're paralleled in a combiner box and I have a fault. Will the fuses in this circuit protect me against this fault at all? And the answer remains no in this case. Important that everyone understand this. Here's the reason why. You have over here the string number 1 contributing 8 amps to the fault directly, not going through any overcurrent protection devices. You have string number 2, which is going to contribute 8 amps through its fuse, and then it's going to backfeed the fault through the fuse number 1. and contribute 8 amps to that fuse, but of course that's a 15 amp fuse as we discussed, so it's not going to blow either, and that neither of the fuses will help you in this situation either. And so this is the first lesson for today. If you only have 2 strings on a PV circuit, you don't need a combiner box, and this is reflected in the code under NEC 699A. Occasionally I'll get a request for a 2-string combiner box, and it's just not going to do anything for you. You would land those 2 strings directly on your inverter without any overcurrent protection in that scenario typically. Okay, let's look at another example. Here we have 3 strings of PV modules, and we have a fault on the first string. Will the fuses in my combiner box in this scenario provide me any protection? And the answer here is yes-ish. So as you can see here, we have about 8 amps from circuit number 2, string number 2, and we have another 8 amps from circuit number 3. Though the current goes through their own fuses, but that's not enough to cause that fuse to operate. But combined, it's about 16 amps, which in theory is just enough that when it backfeeds the fault through string number 1, it'll actually blow this fuse. But there's 2 caveats. One, this fuse will blow, but the fault will still exist for the first string. So you'll still have 8 amps of fault current potentially feeding this fault. But at least you don't have the 16 amps backfeeding it, and this is particularly important because this conductor might not be rated for the 16 amps after all the D-rates are applied. And certainly if you have more than 3 strings, it would not be rated. So it won't melt this conductor, and the fuse does its job, but the fault itself never clears in a PV circuit. It's important to understand that. The other thing that's important to understand about this scenario is that, of course, the modules only make this rated current on a sunny day in full sunlight, which typically only happens in the hours around noon in the summertime. So if it's a cloudy day, or if it's raining, or if it's January, and you only have 3 strings in a combiner box, it might not provide any protection at all, the overcurrent protection devices. So that's lesson number 2. If you only have 3 strings, you do need to have a fuse combiner box in your circuit by code, but it rarely adds that much safety to your system, except maybe in summertime around the hours of noon. So let's look at another scenario. Here we have a fault in the output circuit. So this is the circuit that comes from a combiner box leading towards the inverter. And the question here is, will the fuses I have in my combiner box offer any protection against this fault in my output circuit? And the answer here is no. Each string will contribute about 8 amps to the fault, 32 amps total in this scenario, but none of the fuses in the box will see more than 8 amps, and therefore none of the fuses will operate. So this fault will go undetected and uncleared, and yet it's completely allowed by code. So that's lesson number 3. Fuse source circuits do not provide any protection against fault in output circuits, conductors, and yet this is allowed by code, which kind of blew my mind when I first learned about it. So now we have another scenario where we have several combiner boxes, and those combiner boxes are then recombined in what's typically known as a recombiner or subcombiner, or maybe an output circuit combiner. In this scenario, it's very analogous to having more than 2 strings in a combiner box, in that the backfeed current from each combiner box will clear the overcurrent protection device in the subcombiner and provide some protection in that output circuit. But again, I like to note what I call the rule of 4. If you really want this overcurrent protection device to operate properly, it's really good to have at least 4 circuits, so that you have 3 circuits backfeeding that protection device, which is enough to operate the overcurrent protection even in January. That's the rule of 4. And of course, not all inverters have fused subcombiners. Sometimes you have to pay extra for that feature, or you have to buy an aftermarket fused subcombiner to get that protection. So I'm going to move on to the next subject now, delving right into combiner boxes specifically, and how to specify them, keeping cost in mind. So the first common misconception, I have a lot of people that call me looking for a combiner box, and they say, oh, I need a combiner box, and I need this current rating on my box, because I took my short circuit current rating of my modules, I multiplied by 1.56, because everyone knows in solar everything has to be times 1.56, right? Well, actually, no, that's not actually accurate when it comes to combiner boxes, and here's why. That 1.56 number that everyone talks about is actually a combination of 2 factors. that's two D rates. The first D rate is a 1.25 D rate for something called cloud enhancement. And that's basically an effect where on days where you have a mix of sun and clouds, you can have direct sunlight on your panel, but you can also have indirect sunlight that reflects off the clouds and onto your panel, giving you more than full sun, and therefore more than the full sun output current from that solar module. So for that reason, for that scenario, we always apply a 1.25 D rate for all solar circuits. The second D rate is also 1.25, and you multiply the two 1.25s together to get 1.56. But that second D rate is for something called continuous current, which is defined as any load current that lasts for 3 hours or more. And it's not just for solar circuits. A lot of circuits are considered continuous. This includes typically like lighting circuits, which are on for more than 3 hours, have to be D-rated for continuous current as well. And the reason we have this D rate is that conductors and fuses are typically not designed to operate at their full rated current for this amount of time, and heat will build up and it'll overheat conductors or fuses if they operate at their maximum current for continuous periods of time. So for not just solar applications, but all kinds of applications, we multiply continuous currents by 1.25 as a D rate to avoid this overheating. And this is reflected in the NEC 698B. Photovoltaic system currents shall be considered continuous. So if you look at the equation that you would use to size conductors or fuses or breakers, it looks like this. You take the short circuit current of your string, 1.25 for the cloud enhancement, 1.25 for continuous current, gives you that 1.56 that everybody talks about. You get about 13.6 amps per string. Maybe you round up to 15 amps for a standard fuse size. That's how you size the fuse in the combiner box. But for the combiner box itself, you don't necessarily have to do that. So the code says that equipment that's not a fuse or a breaker or conductor might be designed and rated to operate at that continuous current continuously without overheating. A typical device I can think of is a switch, where a switch is built to interrupt current, and that's kind of the constraining the constraint on the switch design, not the ability to handle continuous current. So there's an exception in 698B that says that circuits containing an assembly together with its overcurrent devices that is listed for continuous operation at 100% of its rating shall be permitted to be used at 100% of its rating, i.e. the second 1.25 does not apply, and so you just take short circuit current times 1.25, and you get about 11 amps per string is kind of the rule of thumb. It's a little bit less. It depends on your module, obviously. But around 11, say, is a typical string current when it comes to rating combiner boxes. And so that's lesson number 4. Multiplied by 1.25, not 1.56. This is a common mistake I get all the time. So if you think of that rule of 11, roughly 11 amps per string, and you want to pick a size for your combiner box and a rating for your combiner box, and you have one string, what would the rating of the combiner box be? Well, duh. Okay, but let's say I have two strings in a combiner box. What would the current rating of that combiner box be? Well, if we're paying attention, we'll see that we remember that for two strings, you actually don't need to have a combiner box at all. So what about three strings? Well, here we would need a 33 amp rated typically combiner box. 3 times 11, 33. But remember the danger, if only 3 strings, it's very unlikely that the fuses in the combiner box will work properly. And so it's nice to have 4 strings in a combiner box if you can manage it. If you do have 4 strings, you would need to have a 44 amp rated box, and 5 strings, 55 amps. Again, this depends a little bit on the rating of your module, but typically. Now, I've highlighted with red boxes certain string numbers that I encourage people to specify when they order boxes. And can anyone guess what it is about these values specifically that make them good values for combiner boxes? Well, the answer is it has to do with disconnect switches. So disconnect switches that are found in combiner boxes typically come in standard sizes. 100 amps, 200 amps, 250 amps, 400 amps are kind of the most common switch sizes that you'll see out there. And of course, in the new code, a disconnect switch is required for every combiner box, and it has to be within line of sight of the combiner box. And furthermore, if it's any more than 6 feet away from the combiner box, you have to have a special label with a directory showing how to get from the combiner box to the disconnect switch. So practically speaking, it's almost always easier just to put the disconnect switch in the box to meet the latest code requirements. So lesson number 5 here is to pay attention to standard switch sizes when deciding the number of strings in a combiner box. So if you have 9 strings, it's about 99 amps. That's a great number to maximize kind of the cost of a 100 amp disconnect switch. If you go to 10 strings, which actually I get more requests for 10 strings than 9, it bumps you into the next switch frame size, which is around 200 amp switch, which is more expensive. Similarly, 18 strings is a nice number to come in just under 200 amps. 22 is great for 250 amps. I get a lot of requests for 24-string combiner boxes, which is, again, kind of not an optimal number to put in a box because you end up just over the 250 amp switch rating, which then requires a 400 amp switch, which is both more expensive and much larger switch frame size, and then that means your whole combiner box enclosure has to grow to accommodate the extra space, and it just gets a lot more expensive. And so if you are using a 400 amp switch, I'd say, if you can, go all the way up to 36 circuits in that box to maximize that switch size. So the next topic I'm going to cover now is combiner box safety. So if you're ever up on the roof of a building and you have the opportunity to open up a combiner box, this is what you might see. Starting in the bottom left-hand corner, there's an equipment ground collector. That's where you typically land the equipment ground from the array. Above that is some string current monitoring devices that may or may not be in the combiner box. Above that is a fused input collector, and that's where all the fuses are located. Typically, you fuse just the positive polarity on strings. If you're using SunPower modules, you might fuse the negative. So we actually call that grounded, ungrounded, to be clear. In Europe or sometimes in North America, increasingly, you might end up with an ungrounded on both positive and negative, and then you would have to have fuses on both the positive and the negative side of the input circuits. But this is still the more typical design. That goes going clockwise around my combiner box to the disconnect switch itself. And then from the disconnect switch, there's a terminal where you land your ungrounded output circuit conductors, typically the positive conductors, output circuit conductors. And then next to that is your grounded conductor. That's typically negative. It's typically not fused, as I talked about. And so the question I have for you is, you open this box and you open up the disconnect switch. So the switch is in the off position. What is safe to touch inside this box? So my first question is, this piece of metal that goes between the fused input collector and the switch, it would be safe to touch that piece of metal if the switch is in the off position? And the answer here is no. Hopefully everyone's aware of that. Because those fuse holders are closed in, you still have all the voltage and current potential from the strings through those fuses feeding that piece of metal. So that metal is absolutely live, and you want to be wearing high voltage gloves if you're dealing with the box in that scenario. You could open all the fuse holders and the switch, and then you could isolate that piece of metal if you had to. But then going on to the other side of the switch, so I open up the switch, so I know the input to the switch is live. I open the switch. Is the ungrounded output circuit live and safe to touch? Or is it safe to touch? And the answer here, again, is in most situations it is not safe to touch this piece of metal either. And the reason for that is if you have more than one combiner box in your system, they'll all be commoned at the inverter or in a sub-combiner box. And so the voltage and current from the other combiner boxes in the system will backfeed this point. And I've gotten caught by this before myself, and it was not a fun situation. So just be careful. If you open up the switch, it's quite likely that neither side of that switch is actually disconnected from voltage. The only way to avoid that is to go down to your sub-combiner and pull the fuses out of there in order to and open the switch to isolate that output circuit. The next below it, the grounded conductor, is it safe to touch that? Well, in theory, yes, it would be because that's grounded at the inverter. But in practice, because there's a voltage drop between here and the point of the inverter, and because I don't know if you really feel lucky that they've properly grounded at the inverter, I would never recommend touching this conductor either. The ground tends to be safer, but again, proceed with caution. So lesson number 6 is combiner boxes contain live parts, and often they're live even when you think they aren't. Even if the switch is open, they're still live likely. If the switch is closed and the fuses are open, it's probably still live, so just be very careful. When combiner boxes do fail, it can be quite spectacular, and it can be a difficult electrical fire to extinguish. One feature I'll talk about a little bit I have one slide that talks about SunLink's combiner boxes, where we use a dielectric material on our back sheet that all the components are mounted to avoid the situation where if one live part hits the steel backplate of the combiner box, it causes a short, which causes a fire in your box. I'm going to move on to the next topic, which is how to specify the lugs and terminals in a combiner box. So there's typically two ways to terminate output conductors in a combiner box. On the left is what I call a compression lug. To use this, you would strip the end of the conductor to expose copper, and you would use a crimping tool to crush that lug onto the end of your wire, and then you would actually bolt that compression lug with a certain hole pattern onto a copper bus bar in your combiner box. The one on the right is what I call mechanical lug. For this one, you strip back the copper conductor, you put it into the lug terminal, and you torque down that set screw, and that holds the wire. I guess the main issue with the mechanical lug on the right is that, especially with large conductor wires, large copper wires, they tend to creep over time. The copper is ductile, and they tend to lose their torque and come loose over time. So it's very important if you are going to use these mechanical style lugs that you go back, every 6 months, a year, and just retorque them and make sure the torque value is correct, because they tend to self-loosen over time. Whereas the compression lug on the left will tend to not lose its connection over time, and it actually gives you a more solid electrical connection even just to begin with. And for that reason, a lot of utilities are actually requiring now that you use a compression style lug for all terminations, because they've seen these problems with the mechanical lugs coming loose. The other issue with the mechanical lug on the right is that typically, it might be, say, up to 350 kcmil wires is pretty common for that lug, and so you just have to be a little careful if you're using a large output conductor and it's 500 or 600 kcmil. It might not fit that lug, so you just have to make sure that you have you're worried about the compatibility of the lug. Whereas with a compression lug on the left, it's pretty forgiving. You can get compression lugs that will fit that same bolt hole pattern for quite a large range of wire sizes. The other thing to pay attention to on these lugs is like here on the bottom here, you can see it says CU7AL on this lug. Does everybody know what CU7AL means? Well, the AL stands for aluminum. So if it says AL, it means it's safe to use aluminum conductors on this lug. Some lugs do not say AL; they just say CU, and you should not ever use an aluminum wire in a non-AL lug. Similarly, the CU stands for copper. Almost all of them have CU ratings, although I suppose it's possible to have aluminum-only rated lugs. So that's what the CU stands for. How about the 9 versus the 7? Does everyone know what that means? That's actually the temperature rating of the lug. So the 9 means 90 C rated, and the 7 means 75 C rated. And that's important because when you're sizing your conductors, often you'll use a 90 C rated conductor because you get a better current rating by code with a 90 C than a 75 C rated conductor. But the code requires under 110.14c that the temperature rating of your conductor has to match the temperature rating of the lowest connection terminal. So if you have a 75C terminal on your output conductor terminal, you might not be able to use the 90C rating of your wire. And another thing to pay attention to is typically the terminals on the fuse holders are only 75C rated. So I have people sometimes that send me specifications for combiner boxes, and they say, I want a combiner box where all the terminals are 90C rated. Well, I actually don't know of any touch-safe fuse holder manufacturer that offers a 90C rated terminal. So if you know of one, please let me know. But typically, it's not possible. I just tell people that only the output lugs can be 90C rated. So lesson 7 is just pay attention to terminals for temperature ratings, for the material compatibility, aluminum versus copper, for wire size, and consider the advantages of compression lugs. Okay, the next topic I'm going to talk about is output circuit design considerations to keeping cost in mind. So this is the output circuit conductors. It's the conductors that go between the combiner box and the inverter typically. And if we look at table 310.15, formerly known as 310.16, you'll see that the ampacity rating of the various sizes of conductors at 75 and 90C. Right. The interesting thing about this table is that if you look at the amps rated in the code of the conductor, and you divide that by the actual circular area of the conductor in Casey Miller square inches, you'll see that you actually have the law of diminishing returns. So as the conductors get larger and larger in the table, you actually get less current per amount of area of that conductor. And that's important because when you buy conductors, basically what you're paying for is just pounds of copper on the roof. So what ends up happening is the dollar you pay per amp of current carrying capacity of a conductor goes down the larger and larger the conductor becomes. So you can have a situation where, a number 1 aught is giving you maybe 50 amps per unit area of conductor, but a number 8 would give you 90 amps per unit area. So you actually, you're better off with more number 8s in terms of pounds of copper than you are with 1 aughts. I hope everyone follows that because it's going to lead into my next discussion, which is just looking at free air versus in conduit ratings for copper. So there's 2 tables in the NEC. One is a free air table. If you look at, say, a 1 aught conductor in free air, it's rated 260 amps, which is pretty good. But as soon as you put that 1 aught into a conduit, you got to use the other table, which basically you lost 35% of the current carrying capacity of that conductor just by the fact that that conductor is now in a conduit. If that conduit is going across a roof in a typical solar application, you get to apply an extra special D rate just for crossing hot roofs with conduit. You can lose another, say, 13% in this example of the current carrying capacity of that conductor. So now all of a sudden my conductor that was rated 260 for my 1 aught is now rated 136 amps. And if I took a number 4 and it was in free air, it would be rated 140 amps. So, I've lost almost half the rating of my conductor because of being in conduit. But it's even worse than maybe it appears, because not only do I need twice as many conductors to carry twice the current, because they're of the law of diminishing returns, I'm actually going to end up paying more like 4 times as much for those conductors, not just twice as much if they have half the current rating, because of this diminishing dollars per amps that you get from the code. So one trick I've seen used with some success is open ladder cable tray. If the conductors in the open ladder cable tray are not bundled, so they're not touching each other and self-heating, most jurisdictions will allow you to claim free air for the current rating of those cables. Again, it's between you and your AHJ, but if you can do that, you can really save a lot of money on copper by using an open ladder cable tray versus a conduit. If you do use a conduit, watch the expansion joints. We've seen, when you have long runs of conduit on a roof, they tend to expand and contract as the roof gets hotter and colder, and we've seen some expansion joints failing, and that's caused fires in the past. And so I actually think the open ladder cable tray might even be a safer option as well as a cost-effective one. A couple other considerations when you're sizing the copper is that because of this law of diminishing returns, it's always better to have 2 medium-sized combiner boxes rather than 1 large one and 1 small one. And I have some math here to kind of show how that works, but I don't really have time to go through it in detail. But I think you get the idea that you have 1 very large conductor. It's very expensive. The small conductor is less expensive, but not so much less that it offsets the price of the more expensive conductor. So if you do the math, typically having 2 medium boxes is better than a large and a small. The other thing to consider is to carefully consider at what point you would transition between your string conductors, which are typically a bunch of small number 10, say, to go to your output conductors in the combiner box. Conventional wisdom might say that because in Conduit, and therefore it doesn't have to be outdoor rated wire. It's going to be less expensive wire maybe, but I find often the opposite is true. Again, because of this diminishing returns issue and all the D rates you have to apply, it might be less expensive per foot to just run your number 10s as long as possible before you transition into an output conductor in Conduit. And here I have some math kind of showing how that works out for one example. So lesson number 6 is just to keep the cost of the output conductors in mind when you're designing your system with combiner boxes. I know from experience a lot of engineers will design solar and they're only worried about the NEC code and make sure everything's code compliant, and that's great. But you should really go to your purchasing department, get information on how much it costs per foot for the various sizes of copper wire, conduit, or whatever you're using, and keep that in mind, because you can often save money on the system if you have that information in front of you. So I'm going to move to an example. So here I have a commercial building, and it has 48 strings of solar modules on it. And I have a couple different options that I could choose for how I want to design my combiner boxes. I could have one single 48-string combiner box with all the strings in it. I could have two 24-string combiner boxes. I could have three 16-string combiner boxes. Or I could have a mishmash of a 22, a 17, and a 9, which might fit the geometry of my roof a little bit better, just the way things are laid out. So let's look at the first option, which is the 48-string option. Typically, I don't recommend this because, as we saw, you can't use a 400 amp switch with 48 strings. You have to go to 800 amp switch, which is it's hard to find. It's expensive. It's big. It tends to be prohibitive. So it's nice to try and keep your string count below that 400 amp mark. Option B was two 24-string combiner boxes, which is more reasonable. You can use that would work, but the issue here is, as I mentioned before, 24 strings is just annoyingly a little bit too much current for a 250 amp switch. So it does push you to two 400 amp switches, and as I mentioned, the 400 amp switches are a much larger frame size. It means that your combiner box is much larger, and the number one driver of cost for combiner box is actually the size of the enclosure, so that drives the price up considerably. So I always try and push people to a 22-string box if they can, and not a 24-string box. Other thing to consider with 224s is this what I talked about at the very beginning about the overcurrent protection devices. If you have two combiner boxes in a fused sub-combiner box, the fuses there will never protect you from a fault. Whereas if you have three or more, then you will, at least in a backfeed situation, that overcurrent protection device will operate, at least if it's enough sun. So a good option, maybe number 3, is three 16-string combiner boxes. Let's look at that. That's pretty nice. It's just under the 200 amp mark, which is a nice standard switch size. So there's a lot of good options for switches in that size. Because there's three, the fuses would operate on a sunny day, so it's a little more safe, perhaps, a design. Let's look at the last option, which is option D. Option D is good too, except remember what I talked about earlier about if you can balance the size of your boxes, you're probably going to save some money on your output conductors. So just run the math. If you want to go with this option, it might work well because of the layout on your roof, but keep in mind that you might be penalized when you're actually paying for the output conductors for these combiner boxes. Another thing to consider is where you want to put the combiner boxes on the roof. So you could, for example, spread them out so that you keep your source circuit conductors as short as possible. Or another strategy might be, let's move them all and be close to the inverter, which will keep my output circuit conductors as run as short as possible. And I find that typically the second example ends up actually less expensive if you're running in Conduit, certainly. And it has to do with what I said earlier about just there's so many D-rates once you go to Conduit across the roof that it tends to push your conductor prices up to be very expensive. And so it's often cheaper just to keep everything number 10 USC2 for longer runs. So I'm just going to summarize the 8 lessons that we've learned today. Number 1, if you have 2 strings, you don't need a combiner box. Lesson 2, if you have 3 strings, you do need a combiner box, but it's not necessarily the safest design. It's nice to go to 4 if you have the option of going to 4. Lesson 3, fuse source circuits in the combiner box do not protect you against faults in your output circuit conductor, and yet this is allowed by code. Number 4, remember multiply by 1.25, not 1.56 when you rate your combiner box current rating. Lesson 5 is just to pay attention to the standard switch sizes when you decide how many strings per box. Lesson 6, combiner boxes contain live parts even when you don't think they do. Even if the fuses are open, even if the switch is open, there can still be live parts in there. So just be very careful when you open the combiner box. Lesson 7, pay attention to the terminals that come with that box, both for temperature, for material compatibility, for the wire size that you can use with that terminal, and consider the advantages of compression versus mechanical lugs. And then lesson 8 is keep the cost of your output conductors in mind when you do your design. So try and get that information from your purchasing department, what you're paying for copper wire sizes when you do your layout. I just have one quick slide on the SunLink line of combiner boxes. We have 2 lines. We have the HomeRun Basic and the HomeRun LTE. The main difference being the LTE uses the mechanical lugs, whereas the HomeRun Basic uses the compression lugs. The HomeRun Basic has a few more options in it, like string level monitoring. The LTE tends to be a little bit less expensive. All the boxes use non-conductive dielectric rated backplates to try and avoid short circuits inside the box if a wire were to come loose, heaven forbid. Also, they have the option of surge protection. They always use touch-safe fuse holders. We have options for string level monitoring, for pre-wiring the box and putting connectors on the outside of the box, which is a nice feature. It avoids having to take a torque screwdriver up to the roof to do all the terminals. And they come in a variety of disconnect switch sizes, 100, 250, 400, even 200, really. So I'm going to move on from there. I didn't get a chance today in the time that we had to cover all the topics I would have liked to have covered. Things I would like to have covered include DEMA ratings for combiner boxes, understanding disconnect switches and how they work in solar circuits a little bit more, grounding and bonding, arc fault detection. So these are all topics that we're considering for a future webinar. If there's interest, if you'd like to see a future webinar to cover some more topics, there'll be an email address at the end. I think it's webinar@sunlink.com. Shoot us an email and say, yeah, I'd be interested in that follow-up, and we'll try and maybe schedule a second webinar to follow up on some of these other topics. So that concludes my presentation for today. I'm going to pause here, and I'm going to see what questions came in through the chat window, so just bear with me.
All right, everybody. We've got a lot of great questions coming in, and continue to send them through the chat feature. The first question is, do you have advice if a visible disconnect is required with 90-degree rating?
Yeah, so this is an issue. Some jurisdictions require to have a visible blade, so you can actually see with your eyes whether the switch is open or closed. You can't rely on just having an indicator like this. But those nice blade switches do tend to be not rated for 90C. So ABB actually has a nice one they just came out with. Just recently got its listing up to 1,000 volts. And it has little windows in it that allow you to see the blades inside the switch when they're open or closed. SOCOMEC, which is a switch that we tend to use more, is working on a similar solution where they're going to put a window in their switch that'll allow you to see the blades go back and forth, and you can see if they're visible or not. And I'm not sure. I've seen a prototype. I'm not sure if they have the listing on it yet. But if you're interested in a particular project, follow up with me, and I'll do some digging for you. I think it's coming. I think some of these manufacturers that make this type of frame disconnect switch were kind of caught off guard by some of the utilities, particularly in Canada, I think, requiring the visible blade, but they're getting there. They're going to add the feature to make that possible. Let's go to the next question. Yeah, so I would have liked to have had a slide on this. Maybe I should have added it to the presentation because I knew there'd be a question on it anyways. But basically, in the 2011 code, there's this new requirement that you have arc fault protection, which I think is a good idea. It comes back to this problem that we saw at the very beginning. where you can have a fault in a PV circuit and none of the fuses in the circuit are going to do anything to protect you from it. It's kind of a dangerous situation. So one solution now it's in the 2011 code is to have this arc fault protection device, which basically, if you have an arcing fault, which is the kind of fault that's most likely to cause a fire, it has a certain frequency signature that they can detect on the DC circuit. They can detect that frequency with basically an intelligent chip that detects that frequency and then can recognize that it's an arc fault, and then it can trigger some device to disconnect that circuit. The problem is, as of now, the only device I know that has their UL listing on their arc fault protection is Eaton, I think, and it's kind of coupled with a breaker that's not easy for me to package into a combiner box. And honestly, I don't think they'll even sell it to me a la carte. But I do know of at least one other manufacturer that has a device that's at UL right now, getting certified, and they'll actually sell us the device now. It just won't have the UL mark on it. But if you're willing to live with that situation where you have a arc fault protection in your box, but without the UL mark on it, then that's something we could provide for you. So the other thing about the NEC code is that like in California, we haven't adopted 2011 yet code. We tend to be about 3 years behind. And so I don't see anybody asking for or requiring the arc fault protection. I have seen, like in Colorado, for example, they're already in 2011 and they're asking for it. And I've seen a lot of customers get away with it, basically with this line of reasoning being, everything has to be UL. There is no UL device, so either I got to be not have the arc fault or not have the UL. And inspectors will let some of our customers get away with that line of reasoning and not require it until the UL listed device is available, which should be soon. So again, if you're looking for arc fault protection, just follow up with me directly, and we can discuss some options. So the question is, do we stock 9, 18, 22, and 36 string boxes? And the answer is yes. Basically, we can just grow. Like if we have fuses along the side here, we can grow, just add more strings along the sides, or here if they're in a V formation like here, we can just add more strings up and down. The only limitation, of course, is sometimes it impacts the size of the box. So you end up like pushing up to, like for example, in my smallest box size in the LT line, I can fit 16. If I go to 17, I gotta go to the next larger box size just to physically fit that. And so even though you might work well with 200 amp switch to have 17, you're in a larger box size. But basically, yes, we do stock all those sizes.
The next question is, do you have an option for powering the Modbus device or string level monitoring from the array instead of supplying a 24 VDC?
Yeah, so the question here is if I have string level monitoring in my box, often you have to power that monitoring device, and it needs a 24-volt power supply, and so you end up running power cable often hundreds of feet towards that monitoring device, and it costs you more than the monitoring device itself. And actually, yes, I have found a power supply that allows me to take the array voltage and come up with a 24-volt signal. Right now, it's UL up to 600 volts. They're working on UL up to 1,000. I haven't updated my own report with our listing agency, but we have a prototype, and if you have a particular project in mind, I would love to talk to you about it.
The next question, is it the same rule of thumb for 3 strings into a combiner box versus 3 output conductors into a sub-combiner?
Yeah, so the question here is it the same rule of thumb for combiner boxes, for strings into combiners as combiner boxes and subcombiners. And yes, that's exactly true, right? So if you have 3 strings into a combiner box, this fuse will protect you, but only if it's really sunny out. So it's some measure of protection, but it'd be better to have 4. And similarly, so it's the exact same rule if I have 3 combiner boxes into a subcombiner box, right? I would have backfeed current from the last 2 combiner boxes feeding the first combiner box. Now, of course, I'm assuming that all these combiner boxes have an equal number of strings inside them, right? Otherwise, that might not apply. But ideally, if you want it to be even safer and you want it to operate even on a day when it's not full sun, it'd be nice to have 4. Really, is the safest design. And even then, consider this. Like, I have multiple strings now. Let's say I have 4 more. So, okay, fine, this fuse is going to blow. This fault has not cleared on my roof, however, right? I could still have 8 amps feeding this fault, and basically all this blowing the fuse really does is it does 2 things. It prevents more than 15 amps from going down my conductor this way, which could be enough to melt my conductor. A, but B, it provides an indication that there's a problem, and hopefully, if you have some kind of monitoring system, you can catch it that the fuse is blown, and then investigate and determine that the fault is there and correct it. But you can also see why there's a push in the industry to find safer ways of doing this, either with arc fault or some other system, because it's just not the safest scenario. It's also why Enphase will try and argue to you that you should be using microinverters everywhere to avoid this situation. Okay, I think I'm gonna wrap up at this point. But if you have more questions, I encourage you to email me, and I'll try and help you. You can just email webinar@sunlink.com. I guess for the purposes of this webinar, questions related to these topics specifically, and I'll try and help you. I also want to point out that if you're buying combiner boxes from SunLink, then as kind of a free bonus, you get my help helping you design your system. So I'm always happy if you want to send me your system design, what you're thinking of for your combiner boxes, or you just want me to help you specify what boxes to use. I'm always there as a resource to work through some of these issues. So it's a service we provide, and I always encourage our customers to take advantage of it. I'm going to pass the mic to Brian just to wrap up the last couple things.
Thanks so much, Daniel, and I want to thank you for your time and effort and giving us some great insight into combiner boxes. I also want to remind everyone that this presentation was recorded, and the recording will be posted on SunLink's website at sunlink.com/training. The URL is right there in the bottom right-hand corner of the slide. If you have any questions regarding information on pricing or to get a quote, feel free to email webinar@sunlink.com or call the phone number in the bottom left corner of the screen. Thanks again, everyone, for joining us today. We definitely look forward to having you back again soon for future webinars. Have a great day.